Precision mechanical watches, such as the one you see here, utilize in part the concept of angular simple harmonic motion to keep time. So you have a wheel inside here that has a very fine coil spring shown in much more clarity here, this coil spring, such that the oscillation rate of this ring going back and forth is periodic, very precisely so, enabling the watch to keep accurate time by strictly mechanical means. This is an example of angular simple harmonic motion. Let's investigate further. So, a very nice example of angular simple harmonic motion is the guts of a mechanical watch. And the details aren't so important, but this thing is oscillating back and forth under the torsion, the restoring torque produced by this very fine coil spring. And this, as it oscillates back and forth, this cog moves around and moves this gear and a whole bunch of other things associated with it to move the hands at a precise rate. So that's all fine and wonderful. Let's look at the basic physics. F is equal to minus kx is our starting point. That is what we saw for a regular spring mass system. Well, now the analogy here is torque equals the equivalent of the spring constant is the torsion constant, often symbolized by kappa, but I'm using delta because I can't really distinguish k's from kappa. So I'm going to use delta, and theta is proportional to the angular displacement, just like the equivalent x, linear displacement. So that's the torsional constant, and it's an empirical result that is true in every situation in the same way that this result is true. Now, torque is I alpha, and that means it's I second derivative of the position. Now, let's go ahead and solve for this differential equation, rearrange it a little bit. D squared theta dt squared is minus delta over I theta. Now look at how that is such a wonderful analogy. 2 d squared x dt squared is minus k over mx. Look at the relationship of the structure of this equation.
Hey, if it's got the right form, let's call a spade, or should I say SHM, SHM.
Well, actually, I think we should say SHM, SHM, because that's exactly what it is. Since this second derivative position is proportional to the displacement, then this second derivative of angular position is proportional to the angular displacement. It really does have the same form, so without further proof, we're going to use the analogous considerations for translational or linear SHM to further develop this. Namely that omega, as we've seen with regular spring mass SHM, is the square root of this quantity. Omega is square root of k over m. So now omega equals square root of delta over I. Frequency is omega over 2 pi. So let's go ahead and divide this by 2 pi. So what else is frequency? Oh yeah, frequency is related to period. It's 1 over period. So period is 2 pi square root of I over delta. And that's just a marvelously satisfying little equation for angular simple harmonic motion, period. 2 pi square root of the moment of inertia. As the moment of inertia gets large, period gets large. And as the torsional constant gets large, this gets small. The twisting force to restore this back to its equilibrium position, which it's always trying to do, increases. So we can kind of summarize these equations, and let me not try and overly elaborate so it doesn't get too confusing. But theta as a function of time is cap theta cosine omega t plus phi. Now what does that mean? Well, this cap theta is what we mean by angular amplitude. So here it is as we go to the max position in one direction and max, well, when I say position, angular position in the other direction. So cap theta is an angle. It's a set amount, the maximum angular position from the equilibrium position in both directions. So this angle is a function of time. The oscillating system has a certain angle with respect to the equilibrium that changes in a cyclic manner, right? Cosine omega t plus phi. But this is the maximum value. So that's all pretty simple, right? Now, cap omega is equal to minus, take the derivative, minus omega cap theta sine omega t plus phi. How we can interpret this is to recognize that the angular velocity of the SHM is related to, yes, you can call this the angular velocity, but now it's useful to think of this as being angular frequency, because this thing is oscillating through its complete SHM at a certain particular angular frequency. Remember, omega, this omega is 2 pi times the frequency. So this is a set quantity. This doesn't change. This omega is not the radians per second that this wheel here is moving through. That's what this is. It's a function of time. It goes from plus or minus maximum values of this quantity here, omega cap theta. Omega is the radians per second of the oscillating system. All right, so if you have, for instance, a really high torsion constant of the spring, the frequency will increase, which means the time it takes to go through 2 pi radians will decrease. In other words, this increases. Hopefully that was not too confusing. And finally, we have, for angular SHM, we have this acceleration. We'll call it angular acceleration. And it's just taking the derivative of this, so minus omega squared cap theta cosine omega t plus phi. So if you think about it, at its maximum displacement, just like with regular SHM, it's going to try and accelerate back to its equilibrium position with its maximum impetus, and zero in the equilibrium position, and then maximum again at the other, in the other extreme of the angular amplitude. And so the maximum value that acceleration is this quantity. Before, with regular translational or linear SHM, this was the maximum acceleration toward the equilibrium position. Well, now it just is the value, omega squared, instead of the amplitude, regular A, it's just angular amplitude. So that is our set of equations. That's a nice analogy to regular linear SHM, and hopefully that's reasonably logical, and you'll be able to correlate it with regular simple harmonic motion. Well, let's apply some of these ideas to a little problem here of a thin metal disc pivoting from a thin wire, like a piano wire of some sort, and so this disc is oscillating back and forth in angular SHM. We're going to find the torsion constant in terms of the quantities here. How does the torsion constant relate to period, mass, radius? Well, torque is equal to torsion constant times theta, which is I alpha. So we've already gone through this progression. Let's just carry it out again. That's I times the second derivative of angular position. So d squared theta dt squared is minus delta over I theta. And we know that delta over I is square root of omega, so that's omega squared theta, which is analogous to this whole concept of acceleration. The second derivative of position is acceleration, after all. Acceleration is v squared over r, which is omega squared r squared over r, or omega squared r. And we want to think about omega as being angular frequency because this is a set value of radians per second. Again, not the radians per second of the disk itself. It's angular motion. But rather the angular frequency of the simple harmonic motion, which will be the same number of radians per second as the original analysis of this was a unit circle, and the omega, or the angular velocity of an object in circular motion, that got projected into one dimension. So don't get that confused with this circle. It's very, very different from the unit circle that analyzed this in the first place. Perhaps that's another connection for you to distinguish between these. In any case, then omega equals square root of delta over I. And we know that, well, we can just solve for delta, omega squared I, so let's carry that out. Omega is 2 pi over t, so 2 pi over t squared times I. It's a uniform solid disk, 1/2 mr squared. So let's just do the math. 4 pi squared over 2 t squared mr squared. And finally, we have our torsion constant, proportional to the mass and highly influenced by the period and the radius, proportional to the radius squared, inversely proportional to the period squared. So these two quantities are strongly correlated with the torsion constant. And there's the unit. So that'll conclude our brief introduction to angular simple harmonic motion.